Well, good evening. Thank you. So I'm Andrew Aline, and I'm the Dean of the College of Science and Engineering here at the University of Minnesota. And I'd like to welcome you to the 16th annual. It's hard to believe they're celebrating 16 years, so like a Sweet 16 party that we're going to have here with a very interesting topic. It's the Misel Family Lecture, and it's presented by the William I. Fine Theoretical Physics Institute at the University of Minnesota. We greatly appreciate the support from the Misel and Fine families, and some of those representatives are here, and we really thank them for their support to make this type of an event possible where we're able to have a lecture like this for the general public. And so if you could join me in thanking the Misel and Fine families, just to show our appreciation. Thank you. Thank you. So the Fine Theoretical Physics Institute is a tremendous asset to physics at the global scale, and certainly to the University of Minnesota and to the state of Minnesota. We take great pride in the accomplishments of the faculty and the researchers in this institute. And lectures like these are important not only for all of us to learn from the distinguished speakers, but to help motivate some of our younger students to hopefully look into a career in the College of Science and Engineering. In fact, we're very proud to announce that about 1,600 new freshmen started the College of Science and Engineering, which is our largest class ever this fall, which shows the real interest that young people from across the state and across the country really have in coming here to the University of Minnesota and engaging with some of the minds that you're going to hear from today. Many of these students, yes. And many of those students, we anticipate, are going to have an interest in exactly the kinds of things that you're going to be hearing about in the areas of physics. And we're really excited to see how they go out and make us all, Minnesota, proud of their accomplishments in the future. But you didn't come here to hear from me, so I'd like to turn this over to Alex to introduce the speaker. I'd like to ask the director of the FTPI, Alex Kamenev, to come up and introduce Professor Francis Halzen.
Good evening, everybody. Well, it's nice to see so many people. Let me start from joining Andrew with welcoming you and extending my appreciation to Misel family. And it's only because of their generosity this event and 16 previous events and many future events will be possible. Our today's speaker is Professor Francis Halzen, and he's a very, very special guest. And he's very special in many respects, of which let me mention just two. So first, he is the first Misel speaker in 16 years who drove to the lecture, not flew to the lecture. And that's not a simple point. He's the first speaker from the Midwest. And our previous events could create an undue impression that the big science is done in the West Coast, East Coast, overseas. So I hope today's lecture will serve to rebuke this impression and show, especially to the young people, that the very, very big science can be done right here, close to home in the Midwest. Okay? The second thing, which is probably even more impressive, is that Francis Halzen is a theoretical physicist by trade and by training, and very good one, who is in charge of a very, very big experimental project. And believe me, this is a very rare occasion. So the only historical analog which I could think about is Robert J. Oppenheimer, who ran Manhattan Project, and we all remember how that turned out. Namely, 80 years after the event, people still create blockbuster superhero movies about him. So maybe, just maybe, again, young people in the audience, you will still tell your kids and grandkids, I was at the University of Minnesota at the Misel lecture where Francis Halzen was giving a talk. And a big movie will be created about it. So Francis is a native of Belgium. She received his degrees from Université Catholique de Louvre. Is it right? Close enough. You know, I fake French accent with my Russian accent. He then moved to Wisconsin in 1972, and he is there ever since. He did a very important pioneering work in elementary particle physics, cosmology, and high-energy physics. He published a best-selling book on these subjects, which was first published 40 years ago and still is one of the most popular textbooks on the market. It's an amazing longevity. He received numerous awards for his theoretical contribution and his contribution to IceCube experiment, which he will tell us about today. Those includes Balzan Prize, Prize of European Physical Society for Astroparticles and Cosmology, Bruna Pontecorvo Prize, and many others. And without further ado, ladies and gentlemen, Professor Francis Halzen.
Thank you for this very nice introduction. It's a pleasure to be here, especially because I could drive here. It's really a pleasure to be here and tell you about this project. This is scary now. I'm going to show you my first slide. And to tell you about this project, I have to explain all these things to you. I have to tell you what a neutrino is, then what neutrino astronomy is, then what IceCube is. IceCube is actually the first telescope that managed to do neutrino astronomy. That's simple. Then I will tell you what we actually saw. Because for me, the exciting thing is, after I got to the first 3 lines, we had no guarantee that we would ever see anything. And you can imagine what a relief it is. So I'll tell you at the end, we actually did do some science. So first topic, what's a neutrino? And of course, if you give the stage to a physicist, you're going to get a lecture, right? So here is the lecture. And maybe you know this from high school. And if this is a bit vague, don't worry about it. The world is made out of 3 particles, or that's what they told you in high school: the proton, the neutron, and the electron. And protons and neutrons make nuclei, and then you put electrons around it, and then you get atoms. And then atoms make you and me and everything else. That's the story of particle physics in a nutshell. Well, this is totally incorrect. You didn't get your money's worth in high school, because in the 1930s, it was realized that the neutron could actually change itself into a proton and an electron. And that is called nuclear physics. When you take matter and you change neutrons and protons, that's how nuclear physics happens. And they noticed, this was the famous Cavendish in Cambridge, that if I am the neutron, occasionally the proton and the electron would go this way, would violate all the laws of physics. If some 2 things move that way and I'm at rest, there must be something that moves that way to balance energy and momentum. And so some smart theorist came up with the idea, well, he said it's simple. There must be a particle going in the other direction that balances energy and momentum. So, and he called that particle, he actually called it a neutron, but that's irrelevant. He called it a neutrino. It was eventually called a neutrino. And, but you didn't see that particle. It just was there. Nobody ever saw the particle until 1956. And that's why it's called the ghost particle often. So that's the neutrino. And he said, I've done a terrible thing. I've invented a particle that cannot be detected. Well, that's not true, otherwise I wouldn't be standing here. But it's almost true. In fact, by today's standards, this is called the missing energy experiment. And so the people who did this experiment basically discovered the neutrino, but they couldn't imagine, you know, only 3 particles exist. You had this beautiful picture of nature. They couldn't imagine there was another particle. And but that's what the world is made of. And of these 4 particles, there are more neutrinos than anything else in the universe. But nobody knows about it because they are like ghosts. They don't let their presence know. And so, but from my explanation, you realize they are essential to change neutrons in protons. So no physics, no nuclear physics happens without a neutrino. You can kind of think of as the agent that make nuclear physics happen. And so I won't dwell on this, but this is a short list. Without nuclear physics, oh, I can actually point at this. Without nuclear physics, there was no Big Bang. Without nuclear physics, stars wouldn't explode, and you know, we are made of stuff that's made by stars partly, so we wouldn't be here. Actually, the sun wouldn't shine. It shines by nuclear physics. So nuclear physics is everywhere. But for this lecture, unfortunately, there is another place where nuclear physics happens, and that is protons that swarm around in the universe and in our galaxy. They hit our atmosphere, and when they hit our atmosphere, they interact with nitrogen and oxygen and make particles that decay into neutrinos. And that's a disaster because it means the Earth is surrounded by atmosphere that emits neutrinos. So it's like if you want to do astronomy with neutrinos, it's like you have these clouds that make neutrinos and they are there all the time. And you have to look through them. That was the challenge. That's one of the challenges of IceCube. Another thing, look, I want to point at this thing on the right. You know what this is. You have all seen this. A nuclear reactor, to avoid radiation, is covered with water. And this water is always blue. What this is there are particles coming out of the nuclear reactor, and particles, when they go through water, color the water blue. That's part of the physics we will use to build this neutrino telescope. So remember that picture. I think I already said all that. Okay. So what's neutrino astronomy? You now know what a neutrino is. This is the sky, and I show you this because we somehow, in astronomy, we use this ellipse, and it's a projection of the whole universe in 2 dimensions. And so the ellipse is such that our own galaxy is here. So this is the plane of our own galaxy. This is the Milky Way, which you can still see from Minnesota, but not from Minneapolis. So that's the universe, all the stars that make light in a 2D projection. So it's a map of the universe the way we like to present it. Now, physicists have been very successful by changing the color of the light. This is white light. So if you make the same picture in blue light, this is one example of blue light, then you see this. Well, it's the same thing, but different, right? So the interesting thing is when you change the color of the light that your telescope sees, you see a different universe. If you go to red light, it looks like this. These are gamma rays. These are very high energy particles of light, and you see again, oops, sorry, go back. You see again our galactic plane, and then you see these dots, and these dots are other galaxies far away. And so this game has been very successful, except When you go one step shorter, farther to more blue light, shorter wavelength, the universe starts totally dark. You don't see anything anymore. And so the idea is to look at that universe with a new particle, and that's the neutrino. And this idea is actually very old. I was fortunate enough to know Fred Reines, who discovered the neutrino in 1956. He discovered them by looking at neutrinos coming out of a reactor. And he told me as soon as we discovered the neutrino and realized it was a real particle, everybody had the idea of doing neutrino astronomy. It's just like light, except it's a neutrino, and as you get a feeling, it doesn't interact very much. It doesn't let its presence known. But there's no reason, if you could detect it, that you couldn't do astronomy with it. And so this is another way to look at the sky. You see, this is again the sky. This is how much energy reaches us from the universe as a function of the color of the light, or the energy of the photon, if it doesn't matter. So you see, most of the particles in the universe are what's labeled CMB. That's the cosmic microwave background. There are actually, these are particles, particles that have atomic type energies, and there are 411 of them in every cubic centimeter in this room and in the whole universe. So the universe is not empty, it's full of this, what we call CMB photons. And so that, they win the prize for the most particles in the universe. So if you go here, you see, you go to infrared light, visible light, X-rays. So you see everything coming from the universe, and you get these different maps which you can then correlate. It's a very successful astronomy. Then you come to the gamma rays, which was the last map I showed, and you see then suddenly astronomy dies. The sky turns dark. And that's where we managed to do astronomy with neutrinos. So you see there is some of our measurements. And if you actually see, this is the sky in light at these very high energies or very low, very bluish wavelength. And we actually see more neutrinos than there is light in the universe. And that was totally unexpected. You know, we thought neutrinos are something exotic that come from very unusual astrophysical environments. Nothing. They just dominate the universe. And so that was a really, I come back to this discovery later, of course. But why does the sky turn dark? It turns dark because if you have light, and we at this energies, we think of light as particles, it doesn't matter. If you see light coming from the photon, the light particle, will meet one of these 411 per cubic centimeter and make an electron and positron. This is standard particle physics. But once it transforms itself into an electron and positron, these are charged particles. The universe is filled with magnetic fields. Our own galaxy is filled with magnetic fields. So charged particles begin to bend in magnetic fields, and they lose all their memory where they come from. So if you look at the sky in charged particles, it's totally uniform. There's no information for astronomy. And so that was the idea. If we manage to detect neutrinos from this object, it doesn't interact with anything. We see it from the beginning of time until the edge of the universe. It doesn't matter, it will reach us. The problem is when it reaches us, it's still hard to detect, right? And so, but that's another way of thinking about it. You see, here is a collection of all these pictures of the universe in different forms of light. If you see, and so neutrinos are really the only way to extend this successful science further to the right. And that's what we try to do. So we try to look into this, it's like looking at the dark side of the moon for the first time. And then the question is there anything interesting there? Well, I mentioned there are these charged particles you cannot do astronomy with, but they actually dominate the energy that reaches us from the universe, and they make neutrinos. And that's exactly what we are after, because we know these charged particles have been detected. They were discovered more than 100 years ago, something like 112 by now. And I can remember when, in 1991, a really modest experiment in Utah discovered what we call a cosmic ray, a proton, reaching us from the universe with an energy of 300 million TeV. Now, the highest energy particles are accelerated in Geneva by the Large Hadron Collider. They produce particles of 14 TeV. Nature produces this particle and accelerates it somewhere to 100 to 300 million TeV. But because they are charged, we cannot find out where or how, or didn't know. And so, for instance, if you took Geneva magnets and filled the orbit of Mercury with magnets, that would accelerate this particle. And I don't think that's how it happened, so we'll skip that example. So now, what about building a neutrino telescope? We knew how to build neutrinos, neutrino detectors. This was a standard technique. All you have to remember from this picture, you need water and these light bulbs on the wall. Those are like light bulbs, except they don't emit light, they detect light. So if light hits them, they change the light in an electric current that we can measure. So they're light detectors. So you need water and light sensors. And the problem is I'm a theoretician, I was part of this. We tried to estimate how big a detector you needed. And so we played with this for like 2 decades and decided that this detector, which is the biggest ever built in the Japanese Alps, it actually must be about the size of this room. The result was it's 10,000 times too small. And remember, even if you build it, you're not sure that it may be 100,000 times too small, and then you are out of luck. But we decide to believe this. And how to build a detector like this was already suggested by this man, Markov, in 1960 at a conference in Rochester. And so I won't read what he said, but this is what he suggested. Okay, we start at the bottom there. You see this dashed line, light. That's a neutrino. It's neutral, it doesn't interact with matter. So it just goes, he suggested, it comes up through the ocean. Why would you look at a neutrino to the ocean? Well, it's because if you look up, you see all this mess in the sky and much else. So when you look through the Earth, only neutrinos get through. So when we look at the sky at the South Pole, we look at the sky above Minneapolis. So that was his first idea. Then, if this neutrinos comes in 3 types, but that's not important here. This neutrino, what will it do? Nothing, it just goes through your detector. The detector is just like in Japan. It's water, so you may be here 3 kilometers deep in water and you fill a kilometer cube with light sensors, which you buy in Japan, by the way. And but about 1 in a million times, this particle, except for going to your detector, will hit the nucleus of an atom, hydrogen or oxygen in water, head on. And when it does that, it makes a small nuclear reaction. And what does a small nuclear reaction do? It makes a little bit of blue light, just like the picture I showed you earlier. So blue light, neutrinos, 1 in a million, will make blue light that we detect with these sensors. And then we can reconstruct that we saw a neutrino. But we can also reconstruct where it comes from. Because among these particles it makes a particle called a muon. And this muon, it's not important, it's just a special particle. It travels through the ice at the speed of light for kilometers. So even if a neutrino hits a nucleus far away, the muon can still go through your detector. And because it comes through the Earth, it tells you that it was a neutrino that created it. And it does something else. It emits blue light, like all charged particles in water. But the light in water goes at 3/4 of the speed of light. The muon goes at the speed of light, or practically. So what does that mean? It leaves the light behind. It makes like a boat that makes a shock wave, a bow wave. And so we measure the bow wave, and then we know the direction of the muon, which tells us the direction of the neutrino. So we have a telescope. That was Markov's idea in 1960. And so as I said this, I already said this, this works because this particle can travel a long way, and you can measure this shock wave of light that it makes and reconstruct where the muon came from, which is the whole point of building a telescope. So this is IceCube. We had the idea we started this in the late 80s in Madison, of instead of putting this in water, this was tried and failed, we were going to freeze them deep into the ice in Antarctica, which is obviously much simpler than putting them in the water. This is not a joke, it's true. And we have proven it. In fact, the detectors in the water are still being built now and being developed, while we finished IceCube 10 years ago. So we were right, it was simpler. Although we were also very naive, as you will see. Anyway, in each of these dots, you see these lines, they are kilometer-long dots, and each of these dots is a light sensor. And so you see here, this is a real event. And you see here, there is the neutrino, of course, you don't see it. It makes this muon, and you see the muon, and then it sets off all our light sensors. And you can see by eye where this muon came from, right? And if you use the computer and all the information that we collect, I can actually tell where this muon comes from, in this case to 0.2 degrees, which is by astronomical standards not good, but it's something. It's the best we can do. And if you don't get it, here is the movie. This is a real event. Now what's exciting about it, you see where the neutrino came from, right? So what's exciting about this event, the energy in this event, so let's scale again. The energy of the particles in Switzerland, the biggest thing ever built, is 14 TeV. The energy in the detector is 2,600 TeV. And such a particle, such a neutrino, the atmosphere cannot really produce. So this event by itself was a discovery of neutrinos coming from the cosmos. Not quiet, we were just close to what physicists call 5 sigma, but that's not important. In fact, we found several of these events. And so it doesn't want to stop. I hope you liked it. I told you already that this was tried and we started then, and when this experiment failed, I should give credit to these people because we borrowed a lot of their techniques, of course, and they always remained our best friend. But we decided to try this in ice, and we were lucky again. At the South Pole, there is a research station of the National Science Foundation that actually has the infrastructure to build such an experiment. And so you can see here, everything goes in there by plane. And you can see there the runway where the planes land. Here you see the South Pole Station, and there you see the IceCube construction at the other end of the runway. The South Pole is there, and as you can see from this cutout here, you're standing on 3 kilometers of ice, 2.5 miles of ice. And so about a bit less than a mile deep, we put this kilometer cube detector. That was the idea. And so the way you do this, you build the stuff in Madison in something called the Physical Sciences Laboratory. It goes by ship or by plane to Christchurch. From there is a logistics center. Everything goes to McMurdo Station. That's a 9-hour flight. And then from McMurdo to the South Pole, which you see here, is another 3-hour flight. So this is a picture of the South Pole. It was actually made by one of my friends, and it's a desert. There's absolutely nothing. If you look to the other side, however, you see there is this station. And the good thing about this station is it has people in it and provides support for this experiment year-round, winter and summer, so you can run your detector. And this is where we got really lucky. Everybody thought this was kind of a cute idea, but would this ice be clear enough to build a particle detector? Usually, you build a particle detector about in a medium that you understand very well, right? Where the light travels far. Because if the light doesn't travel very far in the medium, then you have to put many sensors to cover a kilometer cube, and you cannot afford it. And so we got this incredible surprise that when we started studying that ice, how did you put lasers and LEDs and everything in the ice and try to figure out what its optical properties are. This ice traveled, the light traveled for hundreds and hundreds of meters. So you cannot actually build in the lab, no engineer can build a solid that's as clear as this. And the simple reason is, this is 100,000-year-old snow, frozen. And it's ultra pure and ultra transparent. That's all. And so that's the other reason I'm standing here. Without this big piece of luck, I wouldn't be standing here. And then you imagine now you go to the National Science Foundation, you come back with millions of dollars and start this big project. That's not how it happens. So it shows, I mean, I like this part of the story. This place is actually the room where my theory group had a ping pong table. And so we removed the ping pong table and we had a lab. And we built this, you see these are what's called photomultiplier tubes. These are the light sensors. And in fact, they all worked. And this was the whole collaboration. In fact, we started with 3 people. Here it had already doubled. But that is this big project. That was it in 1993. And these things went actually in the ice and took data until 2008, when we finally cut a cable. And so that was the beginning. And so what are these light sensors? They are photomultiplier tubes. They exist since World War II, and we bought them in Japan for $1,000. That's the easy part. The difficult part of the experiment is that you have to put the sensors in the ice. And that was quite a challenge. And you don't go and ask an engineering firm to build you a drill. In fact, we started developing this project, but the real breakthrough we got is when in 2000, we built a small detector out of these light sensors you saw, and you see here, you now know what this is. We actually could detect neutrinos. And so we found 17 of these events and peddled them in Washington to give us more money to build a bigger detector. And in fact, we saw quite a few more in the meantime. But you see, this was for me the most exciting time of this project. This crazy thing had actually worked. So you're not doing astronomy yet, but actually, you know, the idea that this was the way to do it was not foolish. And it was not always that easy, and this is not me. So we don't, you know, how do you peddle to NSF? You publish something in Nature, and with your 17 events, you make grandiose claims that you are going to build a kilometer cube detector, right? And that's what we did. And we got some help. The Economist, you see, liked us, and that became our logo, actually. And so then it became an industrial undertaking. We put more photomultipliers in the ice. And so if you could go into the ice, remember the Japanese detector I showed? This is the same thing. It's water and ice, actually, and light sensors. And you see this string is a kilometer long. It starts about almost a mile below the surface. And then from the bottom, there is still like half a kilometer to the bedrock. At the South Pole is on solid ground, 3 kilometers of ice on solid ground. So you see there are 60 sensors on this line. If you look further down, 125 meters away, that's about to where the shops are across the street there from here. There is another line like that. And if you put 86 lines in, you fill a kilometer cube. And then you have a detector that looks like that. You see, this is the surface. There is something there which I won't mention tonight. But here, this is a kilometer cube of ice with 5,160 sensors. And so then the question is, what do we see now? Now, to avoid all the questions from now on, how do you put light bulbs in the ice? So I'm going to avoid all these questions by showing you a 2-minute movie. And so the top layer, the first 100 meters is snow, so you just melt it. That's the easy part. Then you reach the solid ice, and then you've got what's called the hot water drill. And this is just a nozzle, and this nozzle puts out boiling water under pressure. And it just falls through the ice, and 2 days later, you have transformed ice into water over about a width of a hole that big. And ice is an insulator, so that water doesn't freeze very slowly. So during that time, before it really refreezes, you put your sensors in, and then they refreeze and they are there forever. So here is the movie. So it's like a circus train, except that the pieces are on sleds. So this is a hose that brings down this hot water in one shot. It's 2.5 kilometers long on this reel. And so this is the power plant, almost 5 megawatts. It's like 40 car wash heaters, that's all. And so it's driven by normal fuel and turbines. And so after 2 days, the drill comes out. So you have your liquid hole there with liquid water. And so in the next frame, you will see that go somewhere else to drill another hole 86 times. And ready there in boxes are these light sensors, 60 of them. And so you actually make the detector in real time. So what happens, of course, they're in pressure vessels. You see there is a cable, and every 17 meters you attach one of these things, and they go down in the ice, When the kilometer is instrumented, you just let it sink to the bottom, and then you wait until it refreezes, and then you take data. It's that simple. Here you see one season, they had drilled 20 holes, and the cables go into this two-story building that you saw on the picture in the beginning, the artist drawing. And in this building, there are computers. And these computers collect these light signals and put them together in these beautiful events that I showed you. And so I'm going to show you a picture now of what IceCube sees. Now remember, IceCube sees neutrinos, and these neutrinos, and muons actually, not just neutrinos, they come out of the atmosphere at a crazy rate. We see our clouds most of the time. And so, so here you see the detector detecting muons. And so the computers at the surface collect these signals, and they can put them together in these beautiful tracks that some of them that come from neutrinos, and some of them don't come through neutrinos, they are just made in the atmosphere. This movie is 10 milliseconds long. So we actually reconstruct 3,000 every second. Not that we want to, but that's what nature gives us. And these are not the ones we are interested in. So now the question is, can we find anything in this mess, right? And so that's the bottom line. So in a year, we detect 10 billion, 100 billion muons. Only 100,000 are really made by neutrinos. And so we are looking into this for neutrinos that come from outside the atmosphere. And so you make this detector run, and of course you don't see very much. And just at that time, New Scientist, this is a very respectable journal, published this thing on its webpage, and you could actually, this is Britain, you could actually bet on whether large projects would be successful or not. And you can see here, LIGO, the chance of detecting gravitational waves were 500 to 1. The LHC discovering the Higgs was 6 to 1. And we discovering cosmic neutrinos was also 6 to 1. I've never been as depressed in my life as I saw this. I said, 6 to 1 after all the work we did. And, but we actually didn't know. And we all started betting on LIGO, and they took the page down. But imagine, all these things have become true. We were really lucky in the last 2 decades, right? That's, I really was not that depressed. I thought, and I won't go through this slide, but if you build something that unusual, you will do something interesting with it. To hell with neutrino astronomy. So what were we doing? We looked originally, the detector goes on, we looked for the simplest thing we could look for. And this is actually, I can explain this. You see there is these protons that you cannot do astronomy with because they swerve to the universe, but they also hit this 411 photons per cubic centimeter. And sometimes they will make a pion, and this pion will decay into a neutrino. And so that's totally calculable, and we call them guaranteed neutrinos. And they are so big, so energetic, that you just look at the events, and when your whole detector fills with light, you found one. In fact, we've never found one. And we begin to understand why the calculations were not wrong, but there were some problems with it. Anyway, before we got any desperation, we found this event. And this event, you don't see a muon track, it's one of these other types of neutrinos, and it has an energy of 1,000 TeV, 100 times the LHC energy. And that we were rather sure that couldn't be produced in the atmosphere. In fact, we found another one of these events and published them. But then the idea was, when we had 2 years of data, let's just forget everything else we are doing. Let's look at 2 years of data and see if there are more of these events. Even they are not what we're looking for. And if you want to have a feeling of how spectacular these events are, is the event I just showed superimposed on the campus in Madison. So actually the data center of IceCube is here, a block from the Capitol. And that's in reality how big this event is if you superimpose it. It's like 5 city blocks wide. And so we found 26 more, and we published. And what do? You published in Science, of course, and that was the publication, and we claimed we had discovered cosmic neutrinos. 2 weeks later, literally, we were awarded the Breakthrough of the Year. And after that, I didn't sleep for many nights. Because I remember there was a press conference, and I can answer any question on this without thinking, right? I've been doing this for too long. The only thing I thought about, what if the next press conference we have to explain why this was wrong? Anyway, it wasn't wrong. And this was not the way we were supposed to do astronomy. I won't go through this slide, but this is the real discovery. It's now close to, there's no statistics question anymore. This is the number of events as a function of their energy. And you see all these events come from the atmosphere, and we reconstruct and measure them very carefully. And then at some point, we see an excess. These come from beyond the atmosphere. Those are cosmic neutrinos. And so these we now could study. There were 2 surprises. The first surprise was, here you see, this is what 1 year of data looks like. If I show you 10 years of data, it's just colored blue. We detect about 138,000 neutrinos, and about 200 of these are cosmic. You're welcome to try to find them. In fact, if you look at the events, the strange thing about it is, we look at the northern hemisphere, and this map is totally uniform. We do statistical tests. They come from everywhere, totally uniformly. What are you supposed to see? You're supposed to see the Milky Way. So we see the rest of the universe. We don't see our own galaxy. And I think we begin to understand why. Remember, that was the shock. I showed you the Milky Way in gamma rays and in light, as you see it. Nothing. In neutrinos, they come from other galaxies. Our own galaxy is a neutrino desert. Because you're first supposed to see neutrino, these accelerators I talk about, in your own galaxy, not in galaxies far away. And even if you add them up, your own galaxy still dominates. It's simple geometry. Okay, so I don't know why that slide is there. I won't spend more time on this, but the other shocking discovery was how large this flux was. This is not boutique science of some special stars or accelerators. I mean, these neutrinos dominate this extreme universe that you cannot see in photons. That's what's shown there. You see, so I think I said all this, so nothing but surprises. The other question was, where do they come from? Somehow they didn't come from something in our own galaxy, mostly. So where did they come from in other galaxies? And we spent about 6 more years, totally frustrated, finding nothing. And then in 2017, September 22, 2017, you remember this now, you can open the phone of half of our collaboration. We saw this event. And in desperation, what we did is, it's like throwing your data overboard. This event, we sent telegram, astronomical telegram, to the whole world, to all the telescopes in the world. We discovered the neutrino, and it comes from there. And so then, we didn't know if anyone paid attention. But after this event was sent around, the coordinates, this is the telegram, it tells where it's come from, that's all. And yeah, so we actually sent this data out, including the analysis, in just 40 seconds after the light travels through the ice. We tell telescopes there's a neutrino coming from there. It actually came from something astronomers call an active galaxy. And these active galaxies have names according to catalogs. It's called TXS 0506, it doesn't matter. It's a galaxy, and it was known to be flaring actually in gamma rays. And the fact that this is accidental is like 1 in 1,000. So it's not 1 in 1,000 happens, you know, when you try hard enough. You're sometimes lucky when you shouldn't be. And so, but then what made this a real event is what happened afterwards. So it was seen to be an emitter of very high energy TV gamma rays. And that made the plot thicken. And to make a long story short, yeah, I want to show this. At some point, more than 20 telescopes were looking in this direction. And the most interesting one was a Russian telescope we only found out about much later, who actually was looking at this source and discovered a flash of light 2 hours later, when this source had not done anything for 15 years. And so that association in time was totally, it's 50 sigma actually. I don't know what that means, but it means it's real. And so we actually then found it in our own data. We went to look in that direction in 10 years of data and found that it made a huge birth in 2014 that we had not missed, but that we couldn't really claim as a discovery. But now that we know where to look, we could claim it as a detection. Anyway, so there it is. So this is our last, so this is 2017. This is September 2017. This is what I've been talking about. So we looked through our data, and this is what happened in 2014. So anyway, so this is another proof. So what happened since then? Well, in our frustration, rather than throwing our data overboard to the rest of the world, we made some wise decision, and that is, we reached this point. This is 10 years of data. We published what we saw. And there was one source in the sky, NGC 1068. It's again one of these active galaxies. What it is, it's a galaxy that has a big black hole at the center, just like our own. But our own black hole doesn't do anything. It's dead. In those galaxies, it's eating its own galaxies. Stars, gas, everything falls into the black hole. And we can actually, this galaxy, we could actually prove that at the center it had a black hole that had surroundings that were just right to produce neutrinos. The sad thing is when we published that, it's 2.9 sigma. And it doesn't matter. You have to reach 3 sigma to claim evidence. And so what do? And this is what we did. And I'm not going to go through this slide, just listen to the words. We decided to recalibrate the whole detector. So we now know where each individual photomultiplier, each individual sensor is, and we know in detail how it works. They are all different. So we start using the detector modeling every single of these sensors separately. Then we used all kinds, we assumed that when you see neutrinos from a source, that the distribution would be Gaussian, which is in a real telescope, it should be. It was not for us. And we actually corrected that. So we were partially blind by using these approximations. And then the big step, we discovered the latest machine learning analysis technique, artificial intelligence. 2 years ago, it made a big jump in power. And we all analyzed all our data, the direction, the energy, everything by neural networks using machine learning. And suddenly, the sky popped out. And I won't go through this. So about a year later, we had a new map, 2 years later. And here, with all these better calibrations, and here you see this spot again. And we were also looking through a list of 110 sources that we had made many years ago, that we wanted to look at individually. And when we looked through this list, we found the same source again. And so the neutrinos come actually from very close to the black hole, for the experts in the audience, like 10 Schwarzschild radii. From the black hole, they are produced. We know this from combination of gamma ray data and our data. And so in the end, we see 80 neutrinos coming from this direction. That was good enough. The chance that this is accidental is less than 1 in 100,000. And so then we started to suspect there was not a good idea to look at gamma ray sources, so we started looking at X-ray sources. In fact, this NGC 1068, which we analyzed in detail, told us that gamma rays don't come out of the accelerator. They appear at MEV energy, but MEV energy, there are no telescopes. So the next best thing is X-rays. So we start to look at X-rays, and more sources popped out. This is not published, but nobody will tell, right? So we saw another galaxy, which is very similar to this one. In fact, these two galaxies were the first active galaxies discovered by Seyfert in 1943. And yeah, it goes on. We now actually even discovered a galaxy in the southern hemisphere where we are not supposed to be very sensitive. It's Circinus, which is again a galaxy like this. The papers are being written. But in this analysis, the first 3 sources were these, which is another galaxy. And look there, the second source that popped out again was the one we found in this multi-telescope campaign. So it was there again. I think I told you it comes from close to the black hole. Theorists insisted it came from something called the jet, which is totally impossible, but they kept insisting, and it's their own problem. But once we discovered this is where it comes from. So this black hole has stuff falling in it, accelerating protons, and these protons interact with gas and hydrogen and produce neutrinos. It's the same method as at Fermilab. That's how you produce neutrinos at Fermilab. And so, most of you must know this picture of a black hole. This is 1 Schwarzschild radii. So our neutrinos come from like 10 times farther away. This is 1.5 Schwarzschild radius. And by the way, this is NASA's picture. I always like to show NASA pictures because if we had their budget to make these pictures, we could have made a better telescope. And so the impression I want to give you is we're on our way. There are active galaxies that accelerate the cosmic rays and produce neutrinos and gamma rays and produce the cosmic rays people have been seeing for a century. But we'll keep going. By the way, we also saw the galactic plane. Here it is in neutrinos. So the galactic plane has been seen in every color of light. We have built a telescope on, but we never saw it. It's actually, this is again a NASA picture, but it's, no. This I have to blame on the German funding agencies. But it's at 10% level of the neutrinos we see from outside. So anyway, this is a continuing story. And I thank you, so stay tuned, read the New York Times, and hopefully we get in there again. Thank you very much for your attention. I didn't do this alone. This is the IceCube collaboration that keeps growing. We are about 400 people now from many countries, but those are the young people that did this work. I mean, I must actually admit, they forced us to do machine learning. I was very suspicious. So the message is, get good students.
All right, we have some time for questions, and we have a couple of microphones down there, so please raise your hands. Yes?
Yes, I think I could not need my phone. A naive question. When the neutrino hits proton and is detected, does it lose any impetus at all?
Any
impetus? Does it keep on going?
No, it just disappears.
Oh, okay.
The question was, what happens to the neutrino when it hits the nucleus? It just dies. And it makes a spray of charged particles, among which this muon. You know, there is a whole zoo of particles, right? That's what I used to do for a living before. And so it disappears and changes itself in charged particles. And the charged particles, those interact with the atoms and make blue light, right? It doesn't do anything because it's neutral. It's just like a photon. Yeah, exactly.
We have young men right there.
How many neutrons come out per hour out of the place that you found they come out of?
Can you repeat it?
Yeah,
How many?
Can you repeat?
How many neutrons come out per hour?
It's very complicated. Oh, you know, the good news is I don't know the answer to your question, and I don't have to. What I mean by that is that we only need this muon. The rest that's happening, this, I told you, when the neutrino disappears and make this nuclear splash of particles that emit light, that the details of that are totally irrelevant to this. In fact, that's happening usually outside your detector, right? And so you cannot measure it. But these details don't matter. All the rest, all the physics we use is, and that's, you know, one of the advantages of this experiment, it all follows what particle physicists call standard model physics. It's all understood. Although the question is, you know, I'm sure occasionally produce neutrons, but how many or how often, someone at Fermilab would know, but I don't. Yeah.
Yes, please.
Oh, by the way, if you want to look at very low energy neutrinos, then actually there is a neutron that recoils when the neutrino interacts, and those are measured, but these are experiments that do neutrino physics, like measure neutrinos from the sun. So sometimes, in our case, it's not important to know where the neutron goes. Yeah.
Thank you for your talk. The question is, have you detected the high energy neutrinos from gamma ray bursts in supernova explosions?
Well, those are two questions. In fact, the big competition among the theorists for explaining the cosmic rays is it active galaxies, are they accelerated by gamma ray bursts? I didn't mention gamma ray bursts because we have never seen one. We have looked at probably 2,000 by now, with one every day, and every day students track the direction and look if there's a neutrino. We've never seen one. In fact, there was a huge gamma ray burst in November of last year. And from not seeing neutrinos from that one, we can actually prove that they don't accelerate the cosmic rays. So I think we have closed that. Now, there may be still, you know, some special gamma ray bursts. We are still looking, but you look for special ones. I won't go into the details. We have not given up on gamma ray bursts. Supernova, that's a different story. This detector is on 100% of the time. We actually have 2 data acquisition systems. We have never been off since 2011 or so. And even then, before that, we ran this smaller detector. And so if a supernova happens in our galaxy, we'll see it. It doesn't matter where. But it hasn't happened. It hasn't happened. And I can tell you it hasn't happened since sometime around 1996. Because if that happened since then, we would have seen it. No way out. Yeah. Yeah, this is actually an amazing achievement of the people who designed the data acquisition system and the electronics of this experiment. It's on 100% of the time.
All right.
In an optical telescope, there are sensors on the mirrors, the mosaic mirrors, to determine stresses as temperature changes. In the sensor that you have, which is a myriad of a kilometer cube, do you have position sensors to determine stressors in the locations of the sensors as the ice shifts?
This thing is frozen in the ice. It never moves. Yeah, that's one of the beauty. We have put 5,000 sensors. You lose some because when the hole refreezes, it's a very violent process. And we lose 1 in 100 sensors deploying them. So that's it. We knew this was going to happen. Since then, we don't agree on the number, but since December 2010, we think we have lost 5 out of 5,100. No, God knows. But 5 is irrelevant, right? If we lost 50, it wouldn't matter. In fact, if we lost 500, it would start to matter. So, and of course, we had realized, I mean, it was not all luck. We had realized that this, if you could build it in ice, if you could develop this drill, which there was actually a genius from Minnesota who was at some point at this university, Bruce Cossey, a glaciologist, who helped us develop this drill. And so once you put it in, you do physics. That's all, you don't worry about it anymore. Now, we did improve the positions of where the sensors are in the kilometer cube. But that's, they don't move, they don't change, yeah.
Is there any sensitivity to or utility of neutrino oscillations at these energies or the scale of the detector?
I don't do that, so I don't talk about it. But no, this is another, I have my next slide, but I'm not going to. You know, about as many people in IceCube are doing this as doing what I've been talking about. We have a detector where there are, at the bottom of the detector, in the center, there are extra strings with light sensors. And that represents about 2 megaton detector to study oscillations. And so we are now happily competing with my friends of NOVA. Some are in the audience here, and we're going to beat them soon.
Right, more questions, please? Yes, there is somebody in the middle.
Hi there. Yes, I was wondering if you have ever thought of expanding the telescope, possibly adding another ring of detectors around the cube, just to get more sensitive data?
No, we are more ambitious than that. We have already developed the telescope. It's a nice story, actually. I'll make very short. You know, we now really understand this detector. We understand the ice. We can model every aspect of the measurements. If you saw the point source measurement, the NGC 1068, our Monte Carlo our simulation of the detector can exactly reproduce this. So now we really know how to build a big detector. And the bottom line is that we can space these strings by a factor 2. And so that means you build the same detector, you make the spacing between the holes 2 times larger, you get 8 times the volume for the same price. This is like the blue light special, is that what they call it? How can you turn it down, right? 10 times the detector for the same, and it actually, seriously, we have a detailed, what's called the technical design, and it was reviewed by the Decadal Review of Astronomy. And as you notice, we are physicists, not astronomers. I was very worried. I got fantastic reviews. So I assume we're going to build this. Maybe not me, there are younger people.
All right, there is a question down here.
Yes.
If you can...
I can repeat it, yeah.
Are you worried about climate change affecting your ice?
No, no, I'm worried about climate change, but not because of the detector. In fact, I'm not sure we know what happens to the ice at the South Pole. I know when we started the experiment, they were trying to measure whether it grew, the ice shelf. You know, you have about 6 inches or so of snow every year, and that compactifies. And so that's how you make this ice shelf. And it was not clear then, I haven't followed this, whether the ice was actually growing or shrinking. And I know they did a satellite experiment to measure this. No, the problem with warming is at the coast. That's 3 hours by plane away, right? Nothing is going to happen.
Yes, please.
Hi, thank you so much for the talk. I was wondering, do neutrinos interact with themselves?
Yes, they do. And for instance, this is obviously not something we worry about because, you know, you see a few a month, they're not going to interact with themselves. But in a supernova, you have a very high density of neutrinos that actually make the supernova expand. In the very, very first stages of the supernova, well, some of them, not all of them, it's dominated by the neutrinos interacting with themselves. So if we ever get a supernova, this will be we'll do more science than anything I've talked about here in 3 seconds, if there ever is a supernova. And that's one of the things we will measure. It depends a bit on what supernova it is, but I'll take any.
Yes, please. In the middle.
How long total did this project take?
What? How?
Can you repeat it, please?
Yeah.
How long total did the project take?
Well, what did it take? Yeah, that's a good, it's a good question. Why did it take so long, right? I wrote my first paper on this I gave my first talk on this in 1986. It took us we built a small detector to show that we could detect neutrinos, even they didn't come from the cosmos, they were our background. And the problem was not building the detector, was understanding the ice. So it took us about 10 years to understand how the ice works as a particle detector. You have to really know everything, but I didn't talk about this. The optics is very complicated. But it doesn't matter whether it's complicated or not. You have to know what it is, and then you're in business. But that took 10 years. And then it took about another, actually we got approved to build IceCube, like within 2 years. Then before the design was finished and the money, took another 5 years. And then it took 7 years to build it. And so if you add all that up, it has been running for 10 years. That's about 30 plus years. And yeah, that's what it took. This was...
Yes, please.
Submerging the detector arrays, did that have any...
I can't repeat it.
Did submerging the detector arrays have any effect on the ice formation and the glass formation of the ice?
No, it's totally mechanical. The question was, does anything, of course, the water that changes back to ice after you put a string in, that ice is different. And that's what we are now working on. We're trying to, in fact, we are almost there. So what's the problem when you do this hot water drilling? You fill that water with oxygen. And these bubbles don't come out, they get trapped. What happens to them? You will never guess, we didn't. They all congregate in a little pipe in the center. And so, yeah. But the details of this, and the rest of the ice looked the same as the old ice that we never touched. But that's the first approximation. The details matter. Yeah, and we are working on that.
Yes, please.
Yeah. If the in-galactic neutrino sources aren't supernovae and it's not the active galactic nucleus, what are they? And also, how much would you have made on the LIGO bet?
How much?
On the LIGO bet for the gravitational.
Yeah. Oh, these are, you know, I can talk here until tomorrow morning, right? You realize that. Okay, galactic sources. That's kind of the last frontier left. We have no idea. And, you know, in astronomy books, you can read that they're supernova remnants, right? There's actually no evidence for this. We look for supernova remnants in neutrinos now that we see them from the Milky Way. And actually, the neutrinos we see, it's all dominated by cosmic rays trapped in our galaxy, making neutrinos on the hydrogen in the plane. We don't see, that dominates the sky. We don't see any evidence for sources. The gamma ray astronomers cannot find any sources either. But, you know, we published the galactic plane result a month ago. So we are only starting. This is a new game now. So maybe I'm back in a year to tell you. But don't get your hopes up.
So we'll take the
last... LIGO.
Oh, sorry. LIGO.
We need, LIGO would be a big success if black holes those black holes don't make neutrinos. But merging neutron stars make neutrinos. So, but we need many of them to have the opportunity to see neutrinos. And it would be a fantastic measurement. And you know, we follow up every LIGO event. But it has been a frustrating story. But, yeah.
All right, so we'll take the last question, and if your question is not being answered, please come to the podium after the lecture. Yes, please.
Have you stored the, over here?
Yes.
Have you stored the information that you, or the data that you've gathered since the beginning of the project? And if you have you already gone back and looked through? Now that you know
I
what you're
didn't
looking
say
for?
this, but yeah, obviously when we did the analysis with we have all our raw data on tape. And in fact, in 2 places. And so whenever we improve the detector, we have a better detector in the future, but also in the past. So we went through all the data. When I said you know, when we got this 2.9 sigma, we started over. Yeah, we used all the data from the beginning. Yeah.
All right, so let's thank Professor Halzen again.
Thank you.